Okay, so we need units to express the digital level. And of course we have RMS, or root mean square levels, for AC signals, and instantaneous levels for waveforms, waveform views, and for DC. So FS, which is an abbreviation for full scale, is the base unit for RMS levels. And it's analogous, so FS is used in the digital domain, and it's analogous to VRMS, or volts RMS, in the analog domain. Now for instantaneous levels, this is the value of a waveform. Audio Precision uses the concept of D. So the positive full scale in the digital domain is +1 D, and the negative full scale is -1 D. And the signal in the digital domain cannot go beyond +1 D and -1 D, because that would clip the signal. It would correspond to clipping, which causes all kinds of distortion. And this is analogous to V, or volts, in the analog domain. So there's still a lot of confusion regarding digital levels. This is the, in English we use an expression called a gotcha, which means customer phones in and he says, I calculated the level in the noise using your FFT, and it's wrong by 3 dB, 3.01 dB. And of course it's not wrong, it's because there's a different convention. So full scale, or FS, is the RMS level of a sine wave whose positive peak touches the maximum code in the digital representation. So for 16-bit, what we call 2's complement, this is a value of 0.7FFF hexadecimal notation. RMS levels are expressed as a fraction of the full-scale reference level. So for example, a sine wave with 1/10 of the maximum level is 0.10 Fs. Now Dbfs is also used, and Dbfs stands for decibels relative to full scale. And the calculation is 20 times the logarithm to the base 10 of the amplitude in Fs. So full scale RMS level is 0 dB full scale, 0 dBFS, or 0 decibels relative to full scale. Fs and Dbfs are always RMS measurements. So it's invalid to express an instantaneous level. When I say instantaneous level, and when the waveform signal goes up and down, if you look at the value of a sample at a certain instant in time, you should never express that in Fs or Dbfs. It's always in D. Now analog levels can be expressed in Fs or Dbfs, and we need a reference for full scale. So for analog to digital converters, the reference is the maximum input level of the device. For digital to analog converters, the reference is the output level for 0 dB full scale input. So in other words, for a DAC, we would output a signal that's 0 dBFS or full scale, and we would measure the corresponding analog level. And in that case, we can talk about analog levels in Dbfs. Now this isn't very common. We don't do this at Audio Precision. What we do is we use one of those references that I showed you in the demonstration earlier, like DBRA or DBRB. So to test the digital to analog converter, we would generate a signal of 0 dBFS. We would measure the voltage, and we would assign the reference to DBRA, and then we would talk about the level in terms of DBRA. So here's an example. We have an A to D converter with a maximum input level of 5 volts RMS. So the reference level is 5 volts RMS is equal to 0 dBFS. Then an analog signal of 0.5 volts RMS is minus 20 dBFS. An example for a digital to analog converter with a maximum output level of 2 volts RMS, the reference level is 2 volts RMS corresponds to 0 dBFS. Then an analog signal of 1 volt RMS is minus 6 dB relative to full scale. Now there are some difficulties with FS and Dbfs. Signals can have levels greater than 1.0 FS or 0 Dbfs. A consequence of using sine waves for the reference. So sine waves have a crest factor, the ratio of the peak value of the signal to the root mean square value of about 3.01 dB. But square waves have a much higher crest factor. So levels greater than 0 dBFS will cause problems later in the signal chain. They can actually reach plus 3.01 dBFS. So that's a consequence of the definition being related to a sine wave. A sine wave with a peak value of 1.0 D has an RMS level of 1.0 FS. So a digital sine with peak P units of D has an RMS level of PFS, but an analog sine with a value of P volts has an RMS level of P divided by the square root of 2 volts RMS. And that was the gotcha that I was referring to later. We keep getting customers calling in and saying, you know, your RMS calculation is wrong because I analyzed the FFT and I come up with a value that's different by 3.01 dB. And of course it's because of this convention. Another point to note is that FS and Dbfs are always RMS measurements. So it's invalid to express instantaneous levels in FS or Dbfs. So here we're showing units of D on the vertical axis, and a full-scale wave just touches it at plus 1 D and minus 1 D. Or a square wave, there's some ringing here because of Gibbs phenomenon, but the signal just touches at plus 1 D or minus 1 D. Another thing to note is in terms of digital peak metering, here we're sampling the waveform at these sampling instants. And in some cases, the signal actually goes higher between the sampling instances. Therefore, we can have an error in the estimate of the peak value of the signal in the digital domain. So sometimes it's important to know the true peak, otherwise filtering and interpolation later in the signal chain may cause it to clip, causing distortion. Clipping means that the signal goes above full scale, and that causes a lot of distortion because you're taking a signal that's a nice smooth sine wave and you're adding, forcing it to be a square wave which has many, many harmonics. So there's an ITU standard, BS 1770-3, that specifies when you want to estimate a true peak of a digital signal, you should use a 4 times oversampling meter, and that allows you to estimate the values in between the sampling instances. It has a worst case error of less than 0.5 dB. Okay, so there are many connector types. We have XLR. These are the 3-pin connectors that are often used in analog audio. The RCA type, BNC, optical, HDMI, and square pins. So the square pins would be when you're working at the board component level and you have to plug these little connectors directly onto pins on the circuit board. So the pro audio and broadcast typically use these balanced connections, and these are some of the cables that we use at Audio Precision. These are 1 meter long digital balanced cables with male and female XLR connectors on each end. Unbalanced is used for typically for broadcast with AES-3 and consumer audio. Consumer audio is often called SPDIF, stands for Sony Philips Digital Interface. And then there are some optical cables in use for pro audio, like light pipe connections, and also the consumer version of this is called Toslink for Toshiba Link. DSIO is for That's an acronym for an interface that we have in our audio precision analyzers called digital serial input-output. And this is for interchip connections on printed circuit boards. So when you're at the development stage and you want to connect to a chip directly, it might be an evaluation board, you connect to these boards typically with these little 2-pin headers that have a ground and one signal, and you use multiples of them for the connection. HDMI is used for consumer audio and video, and we're also going to talk today about PDM, pulse density modulation. That's a topic for later in the presentation. I'm not sure if it's today or tomorrow. PDM microphones are microphones that are typically used in cell phones. So most of the cell phones today have 2 of these digital microphones. And we'll be talking about those later. So first we'll look at the balanced digital connections and the circuit. So we have the female XLR connector and the male XLR connector. They have 3 pins. Pin 1 is the cable shield. Pin 2 is a signal, and pin 3 is a signal. And the relative polarity of the pins 2 and pin 3 is not important. So this circuit has a 110 ohm interface impedance, and the nominal pulse amplitude of the signal carried is 5 volts peak to peak into the load. So you can see a circuit diagram here, and we have the cable shield connected to ground at the 2 locations, the output side and the input side. This is the cables that I held up earlier. So these are the type that Audio Precision sells. They're a Belden 1696A cable, 110 ohm impedance. They have RF suppression. This is little ferrite bead at both ends of the cable for suppressing radio frequency interference. And they're a uniform twisted pair connection inside. And these are the part numbers for the cables that we sell. So they come in, each kit includes 2 cables, one for input, one for output, and they're typically 1, 2, or 4 meters in length. Unbalanced connections for digital I/O use BNC typically. So the standard is AES-3-ID or IEC 60958-4. They have a 75 ohm interface impedance, and the nominal pulse amplitude of the signal is 1 volt peak to peak into the load. And finally, there's the RCA phono plug connections. That's used typically on consumer equipment. We really don't like these cables. The connector, one of the problems with it is when you connect the cable to the device, the first conductor to touch the connection is the signal. And sometimes cables can have a charge built up inside, and you end up connecting a high charge cable to a component, and you can cause damage. It's much better to have something where the ground connection touches first. So these are the cheapest, the least reliable cables. They have a 75 ohm interface impedance and a nominal pulse amplitude of 0.5 volts peak to peak into the load. This shows the unbalanced digital circuit. It's typical of most consumer electronic connections. And you can see if you look on the back of many consumer devices like receivers and that kind of thing, they'll have these RCA connectors. So the signal is carried on one line, and it's referenced to ground or a chassis connection, making this connection inherently sensitive to ground noise. It doesn't have the noise immunity that's offered by a balanced connection. These are adapters that can convert between a balanced and an unbalanced digital connection. And they use an impedance matching transformer. So there's a couple of options here. These are a brand called Canary. They have a BNC to female XLR and a BNC to male XLR. And on the left, there are some Neutrik equivalents. again, which have these impedance matching transformers. So 110 ohm on the balanced side and 75 ohm on the unbalanced side. This is the optical digital connection. So for light pipe, which is light pipe or SPDIF. The light pipe is a semi-pro audio, which handles up to 8 channels. And then the Toslink is the IEC 61607-1 and -2. So it's stereo or encoded multi-channel. This is gradually being replaced with HDMI connectors. So we're seeing these optical connections go out of favor in consumer equipment. A lot of newer devices don't even have them. Because it's optical, ground loops are not possible, and it's not susceptible to RF interference. One of the problems is the cables are easily damaged, so they're not very robust. They have lengths up to about 6 meters total, but the vendor support is quickly disappearing. As a matter of fact, in one of our analyzers, we use an older part that's used for Toslink interface, and it's getting very hard to get the chips used in the receivers these days. Now this is these are the connections for the digital serial input-output interface, and square pins are most common. So we'll be talking about DSIO connections later in the seminar. And these are the cables that we offer. So they're typically, on one end of our analyzer, it's a 15-pin cable that you can see here. It looks like a VGA connector. It's 15 pins, and actually a VGA cable will fit it, but it's nothing like a VGA cable in terms of the pinouts. And we put a lot of engineering into this cable to overcome some of the problems with noise and crosstalk and that sort of thing. So as a result, our cable is quite expensive. But we offer 2 of these cables here. This one has the 15-pin D-sub connector on one end, and then it breaks out to the different 2-pin headers that would plug into different points on the circuit board. And then on the other side, we have this cable, which is meant to plug into the monitor. This is actually plugged into the wrong port in this picture. The signals going to the board should be plugged into the top one, and from the monitor you can take these BNC cables and plug them into an oscilloscope. So you can monitor the different lines like the clock and the frame clock and the bit clock and that sort of thing on an oscilloscope. You can also use a custom cable like this that's a direct connection with a bare wire, and they use short twisted pairs consisting of a signal and a ground connection on each pair of pins. So with DSIO digital connections, there are some things that you don't want to do. You don't want to have a long wire length. You don't want to have inconsistent grounding. You want to avoid high capacitance cables. A lot of devices can't handle high capacitance cables. And then you really want to avoid having branches in the circuit. So this looks like a very bad practice here. We see all of these wires being clipped onto the board with little clips, and you can see these probes attached at different points. And these should really look like nice sharp edges on an oscilloscope, and they don't. You can see that they're very rounded, and this is going to lead to problems in trying to measure this digital audio. So you want to avoid these types of practices. This is a HDMI digital connection. So the full-size connector is the A type, which is very commonly found on televisions and AV receivers. There's a Type C mini connector, and then a Type D micro connector. There's an MHL standard. I think it stands for Mobile High Definition Link. And this will sometimes use the USB connector on a smartphone to double as an HDMI cable. Now this cable carries video and audio in a single connector. And sometimes it has issues with the video quality that can degrade with longer lengths of cable. So we'll be talking more. We have a whole session on HDMI audio that we're going to cover later in the seminar. And then for PDM digital connections, so these PDM microphones typically are mounted on a circuit board. Here's a picture of some, and I have one here that if you want to look at it during the break, you can see it, but they're very tiny. This little circuit board is the size of a postage stamp, and it has 2 microphones on it. The microphones, the PDM microphones have a 1-bit sigma delta A to D converter built right into the capsule, and they're all digital connections to and from the microphone. And they typically work in pairs. So we provide this cable, which has 3 BNC connectors that connects to our analyzer, and then these 2-pin headers, one for the clock, one for the power for the microphone, and one for the signal. Now, one of the issues with these PDM connections is that longer cable lengths can seriously degrade the signal. They can't travel very far at all. And I think B&P International has one of these devices out on the table outside. We'll probably bring it in later. We're going to be talking about PDM during the seminar. And what this does is you can put this between the analyzer and a long cable, and it allows you to drive a much longer length. So for example, if you're testing these microphones in an anechoic chamber, you're going to want to have the analyzer with its fan outside the chamber, and you can use this line driver to use a longer cable to put the driver inside the chamber and not degrade your signal. This graph shows the cable capacity for PDM digital connections when using this line driver. So this curve up here is the cable drive limited. So we're showing the cable length in feet. Apologize for the use of feet, but this 100 feet would be about 30 meters. So this is just about maybe 40 meters or so. And then on the horizontal axis, we have the bit clock frequency. That's the frequency of the bit clock in these pulse density modulation microphones. So for a typical microphone clock rate of 3 megahertz, we would have a length of about 17 meters that we could drive with this PDM line driver. Without the line driver, you have a very short distance available, maybe 1 meter maximum, might even be less than that. So that's something to be aware of. So the digital interface fundamentals topic deals with the AES-3 and SPDIF and Toslink interface. And this interface has been around for a long time. It's very well known and well documented. So digital audio interface formats. We have serial, and most of these interfaces are serial, which means that the data travels in a serial fashion down the line. Parallel interfaces would have 1 wire per bit, and those are very rare. So we have AES-3 Professional, sometimes called AES-EBU, SPDIF EIJ, which is the consumer variant of AES-3, Toslink Consumer Optical, that's the optical connections that we talked about earlier. We have Sony SDIF and SDIF2. I'm not familiar with those myself, I've never heard of them. We have multi-channel interfaces like MADI, which has AES-10 and 56 channels plus. There's the Alesis and TDIF 8-channel, USB and IEEE 1394. So these are PC audio formats used for digital audio. IEEE 1394 is commonly known as FireWire. It's often used on pro audio devices. And then we have I2S. I2S stands for what is inter-chip, integrated circuit inter-chip audio, I think, serial audio. We'll be talking about that during the DSIO part of the presentation, and then other interfaces. So some of the topics we're going to cover in this presentation are kind of difficult. We're really just kind of touching the surface, and I would encourage you to have a look at this book. This is a book, I think it's 140 pages. It's available on our website as a PDF. You can download it for free. It's quite a good reference. So it talks about the digital interface, jitter theory, A to D converter measurements, and digital to analog converter measurements. I have a copy on my laptop here if anyone wants it, but you can get it. You can get it at ap.com as a free download. Okay, so we're going to talk about standardized digital audio interface formats. So these formats both use identical data structures, except for what's called the channel status bytes. The data coding used allows the clock to be extracted from the data stream, and the electrical specification varies. So what happens, it's kind of unique in that the digital audio signal contains the clock as well as the data and what we call metadata, which is little bits of information used to describe the signal, and all of it is encoded into the stream, into the serial stream. So the interfaces are AES-3, sometimes called AES-EBU, and that's according to standard IEC 60958-4. There's SPDIF, that's IEC 60958-3, and the Toslink optical SPDIF based, IEC 61607. So we're going to talk about the common elements of these three formats. So AES-3, as we mentioned during the connections, it has 110 ohm balanced cable with XLR connectors, and the nominal pulse amplitude is 5 volts peak to peak. It's allowed to vary between 2 and 7 volts peak to peak. The AES-3 ID uses 75 ohm video coax cable with BNC connectors on each end. It has a nominal pulse amplitude of 1 volt peak to peak, and it's allowed to vary between 0.8 and 1.2 volts peak to peak. It's similar to a composite video signal in terms of its level and its bandwidth. So a composite video signal would be one that's passed on those 75 ohm coaxial connectors, like for broadcast television and so on. There's the professional channel status bit interpretation, and we'll be talking about that more during this presentation. And the sample rates vary from 22.05 kilohertz to 192 kilohertz. The most common one being 48 kilohertz. Now, SPDIF consumer stands for Sony Philips Digital Interface. It was accepted by the EIAJ, and it's now an international or IEC standard. Uses unbalanced 75 ohm coaxial cable and RCA connections. The nominal output voltage is 0.5 volts peak to peak. The Toslink optical uses the same data protocol, and these two interfaces use what we call the consumer status bit code interpretation. So when working with these interface signals, it's important to realize that it's not audio. It's basically a square wave. The connection rules are similar to working with composite video. So a termination is required. You have to manage the termination impedance, and you can't have any splitters in the connection. A signal to several locations has to be serially connected to one device at a time, and termination only at the far end. For larger systems with a distribution amplifier, for larger systems, a distribution amplifier can be used, as is done with a video reference, but you have to terminate each source. One thing to note is that long cable runs can degrade the signal substantially. So an AES-3 balanced cable requires good quality 110 ohm cable, and cables longer than 100 meters are risky. The AES-3 or SPDIF unbalanced can use 75 ohm coax cable, and you can have lengths, cable run lengths of several hundred meters. So one of my colleagues was telling me that we had a situation in the United States. There was this big show going on, and one of our guys happened to be at the show, and he had an audio analyzer with him, and I think it was a famous performer, Celine Dion, that was performing. And they called our engineer in and said, hey, we're having a problem with the audio signal. He took his analyzer in and looked at the signal, and he found that the interface signal had degraded substantially. And what had happened was they were running this AES-3 balanced cable for hundreds of meters. So they ended up using a couple of those transformers, impedance matching transformers that I mentioned, and using coaxial cable, and they were able to continue with the show. So something to note, you can't run these balanced connections for very long distances. So in this interface, digital words are assembled into serial frames of data. The signal has two channels of data, typically left and right. It's meant for sending stereo audio. And subframes for left channel A and right channel B are assembled in a sequence into a single bit stream. Each subframe or field contains 32 bits. The frame rate is the A to D converter sample rate. So at 48K samples per second, or 48 kilohertz, each frame lasts 20.8 microseconds. So that's 1 over 48,000. And a total of 64 bits of data are included in each frame. So the bit rate is 3.072 megahertz with a 48 kilohertz clock rate. Now there is administrative data inserted into the stream. There's a preamble at the start of each subframe or field for synchronization of the receiver. It's also called sync. And each data group has a unique preamble. There are 4 bits. Each bit, so the bits represent validity, user, channel, and status, channel status, and parity. And those are abbreviated VUCP. So they're inserted at the end of each subframe. So if we look at the preamble, you can see we have this preamble up here. There's the A data, these VUCP bits, then the Y preamble and the B data and VUCP bits at the end. And the VUCP stands for validity, user, channel status, and parity. So the subframe or field is 32 bits long. So in order, the preamble has 4 bits for sync and identification. It has up to 24 bits of audio data, and the audio data is sent LSB, or least significant bit, first. The most significant bit, or MSB, is the analog signal polarity bit. The first 4 least significant bits are auxiliary bits and are available for other data if the audio is less than 20 bits, less than or equal to 20 bits. So if you're not using the full 24 bits for your resolution, you can put some administrative data encoded inside. And finally, you get the 4 VUCP bits for administrative data. So the 24 bits of audio data and the 4 VUCP bits are encoded using what's called biphase coding. This is also called transition or Manchester coding. So every bit period starts with a transition. And these are just some rules about the interface. For a bit value of 0, there is no transition within the bit period. If the bit value is 1, there is a transition at half the period length. So here's a picture of what a stream might look like here. So this The top graph just shows a logic input. So we have a 0 and a 1 and a 1 and a 0 and a 1, 0, 0. With this biphase coding or Manchester coding, the signal gets represented like this. So you can see wherever there's a 1, there's a transition within the frame. And when there's a 0, there's no transition along the sampling instance. So it's just a way of taking the logic level and converting it into this biphase encoding. And there's some advantages to encoding the signal that way. For one thing, it allows the system to reconstruct the clock that comes along with the data. And it has some other advantages as well. Now these advantages are, it's not polarity sensitive. So the cable conductors can be reversed without any change in the data. There's very little DC in the signal, so it can be transformer coupled. The signal remains vertically symmetric about the slicing point. But there is occasionally some problem with short-term effects. The signal data can cause some jitter. And we'll be talking about this a little bit later. So the preamble is to have a unique identification code, identification and sync signal which can't accidentally occur in the data. The preambles violate the biphase coding. The preamble always includes a 3-unit interval long pulse. The 3 UI pulse only appears in the preamble. So this unit interval, if we back up to the signal here, you can see that this represents a 1 in the biphase coding, and this little half of a time slot is called a unit interval. It's the smallest interval that is needed to represent the data at the physical layer. So the preamble always includes this 3 UI long pulse, and this pulse only appears in the preamble. And there are 3 preambles defined: X for professional or M for consumer. That's the channel A data. Y for professional or W for consumer. That's the channel B data. And Z for professional or B for consumer. And that's channel A and the start of the data block. So here this graphic shows the XYZ preambles. So you have the start of A subframe when not at the start of a block. So the X preamble is 3 unit intervals and 3 unit intervals. The start of the B subframe, 3 unit intervals, then 2 unit intervals, then 1, then 2, and the start of a channel status block and the A subframe. So that's the Z preamble. The administrative data, VUCP, is 4 bits at the end of each subframe. So V for validity bit is sent by the transmitter to indicate valid information. Each subframe is separate. The user bit can be used as desired. We'll talk a little bit about the user bit in a few minutes. The channel status bit contains the administrative data. And the U and C parts of the VUCP code use the data across the entire block length, 192 times 2 bits. So a channel status block has 192 frames, and when you take these U and C bits from each of these 192 frames, you get 192 bits for each of the user bits and the channel status bits. The parity bit value is 1 if the sum of the audio data bit values in the subframe is odd, 0 if it's even. So the transmitter sets this parity bit, and at the receiving end, the receiver will sum up the values and check it against the parity and try to detect an error. And only odd numbers of errors can be detected. So this shows the status bits, the bytes, and the blocks of data. So you can see here we have channel A. This would be frame 0 with a Z preamble, then a Y preamble, then X. And the channel status block is going to be 192 frames long, or 4 milliseconds at 48 kilohertz. And within the stream we have the VUCP bits. And when we assemble, we pull the bits out of these U and C values for all 192 frames. We would get 192 channel status bits and 192 user bits. So what can go wrong with the digital interface? The sample rate can be incorrect. The pulse amplitude on the interface can be degraded if the voltage is too low. This can happen due to long cables. The pulse rise times and fall times can be degraded. Instead of having nice sharp edges, they can have sloped edges from long cable resistance and capacitance characteristics. There can be interfering signals and noise. So normal mode affects the balanced and unbalanced connections, and the common mode can affect the balanced connections only. There's also jitter of the clocks, which we'll talk about in the next topic, and then synchronization problems. Now there's a, if you look at this, the physical layer signal on a high-speed storage oscilloscope, you get this view which is called an eye pattern. And you can see here we have 1/2 of a bit period, and the minimum voltage here is 200 millivolts minimum and a bit pattern. This shows the influence of all the signal degradation, amplitude, rise and fall time, noise and jitter, etc. The AES-3 eye pattern minimum is 200 millivolts peak to peak amplitude and a period of at least half the 1 UI pulse width for the sample rate in use. And you can see how there are many samples overlain here, and they're not one on top of the other. The variations of the zero crossing point of the pulse's jitter. So some eye patterns display the inner envelope, which is the worst case. Jitter is also a potential defect in any pulse train. So it's the time difference between the actual zero crossing of a pulse versus the theoretical zero crossing of the pulse. So you want your pulses to be your rock steady, and if there's jitter on the clock, the transitions move back and forth in time, causing errors in the sampling. So jitter on the clock signal of an A to D or D to A converter can cause problems. Clock jitter can cause the signal to be sampled too early or too late, resulting in amplitude errors. Digital to analog converter clocks must be locked to the digital input sample rate. Depending on the circuit design, jitter on the digital input may introduce internal clock jitter that affects the D to A converter. There's also a possibility of data-induced jitter, and this is kind of a unique thing about this interface. So cables have resistance and capacitance, and depending on the data that occurs in the stream, it can cause the capacitance, the charge stored in the cable, to increase or decrease, just depending on the pattern of bits that come in. So depending on this variation of 3 UI, 2 UI, and 1 UI pulses, the vertical center line of this average value can wander up and down, and this causes the sampling instances to change, which causes jitter on the clock. So the wandering up and down of the center line is a short-term DC offset of the signal. The result of this short-term wandering up and down of the center line is that zero crossings arrive slightly early or slightly late, depending upon the sequence of data, which is in fact a type of jitter. This early-late arrival causes jitter in the zero crossing detector in the receiver because of the short-term DC offset. This occurs due to reduced bandwidth, even if the transmitting clock is perfectly jitter-free. So just the data, the pattern of bits in the data, can cause jitter on the interface. This this graph shows triggering on the X preamble and overlapping several traces. And you can see the jitter in the zero crossings. They were wandering back and forth a little bit in time. There's a special test for this, a signal called the J test, which is, it's talked about in the book that I showed you earlier. And this J test signal is designed to maximize the effect of this data-induced jitter. So it's often used with analog devices like CD players, for example, where you can play this signal out over the analog output and use FFT analysis to look for jitter artifacts in the incoming signal. So that's it for the digital interface fundamentals. I'll just show some of the settings in the analyzer here. So let's see. We'll change our input-output panel to go, let's look at digital balanced. And actually, why don't I think what I'll do is connect a cable directly. So I've set the output to digital balanced and the input to digital balanced, but you'll notice I haven't connected a cable yet. And in this green on black indicator down below, it's showing that my output is digital balanced with a sample rate of 48 kilohertz. On the input side, the input is digital balanced, but there's a big red indicator showing that the sample is unlocked. So there's no cable connected, no signal coming in, and the analyzer is telling me that it's unlocked. So once I plug the cable in, you can see that the incoming sample rate is showing down here at 48 kilohertz, and the signal is locked. So when I'm set up here in the digital domain, let's go back to monitors and just turn on a signal. And it looks like we have an A-weighting filter on. Let's turn that off. So I have some controls here that I can use to get at the digital interface. You can see here, we talked before about the bit depth. I can change the sample rate, and system changes accordingly. Go all the way up to 192K. Now the metadata that we were talking about can be accessed through this control here, status bits and user bits. And there's also, this is on the output side. So by default, everything is set to auto. There's also a meter over here, which is for the digital input side. And this is metadata that's carried in those user bits and channel status bits that occur in those channel status blocks of 192 frames. So if I uncheck this, you'll see here we have access to these fields, and I can change a field here, like change this from consumer to professional, and we're getting an indication that the sampling frequency is incorrect. If I change the sampling frequency to 192K, now that indication has gone away. So if you want to, you can change some of these status bits for subframe A and subframe B. By default, they're tied together, but you can change them independently if you like, and try some different things out with your audio. You can also play with some of these controls. If you want to change the cyclic redundancy check for channel A and so on, and then you have access to the various status bits and the user bits. So let me go back to Auto Professional. Actually, I want to change this to subframes A and B are the same. You also have controls over the validity bit for A and B. You can set them to valid or invalid. And you can see on the input side we're picking that up. These are good tools for debugging the interface. You can also introduce a parity error. And that should show up on the input side as well. This will allow you to introduce some noise on the physical interface. And you can introduce a common mode sine voltage across the two connectors of the balanced digital interface with a different voltage. You can also change the, you can enter cable simulation mode where you simulate a long cable being attached to the signal. And then there is a custom rise time where you can specify the rise time of the pulses on the interface. This would be used for testing digital input devices. And you can invert the signal.